So far we found that if p and q are prime, then phi of p is p minus 1, phi of p to the n is p to the n minus 1 times p minus 1, and phi of pq is p minus 1 times q minus 1. And we have reason to believe that if the greatest common divisor of p and q is 1, where p and q are not necessarily primes, then phi of the product is the product of the phi values. Now, when we found phi of 36, we factored 36 as 4 times 9, a product of relatively prime numbers. We set down a grid with 4 rows and 9 columns. We eliminated all columns whose lead number had a common factor with 9, and then eliminated entries in the remaining columns whose numbers had a common factor with 4. So let's try to do this generally. So suppose n is pq, a product of numbers whose greatest common divisor is 1. So we can set these numbers down in a grid with q rows of p elements. Our first step was to eliminate all columns whose lead numbers had a common factor with p. While that worked in the concrete case, will it always work? Well, let's see. So consider the numbers in any column. They'll be r, p plus r, 2p plus r, 3p plus r, and so on. So suppose the greatest common divisor of r and p is some number d not equal to 1. Then the greatest common divisor of p plus r and p will also be not equal to 1. And in general, the greatest common divisor of any multiple of p plus r and p is not going to be equal to 1. And what this means is that all entries in any column whose top number is not relatively prime to p are also not relatively prime to p. So they definitely won't be relatively prime to pq, and we can ignore them. This leaves phi of p columns. Now consider the entries in any column remaining. These will consist of the q values r, p plus r, 2p plus r, and so on. At this point, we'll note that sometimes every problem is a nail. We've been reducing numbers mod n for quite a while. No reason to stop now. If we reduce these numbers mod q, we'll get values from among the possible values mod q. Could two of these values be the same? Well, let's suppose they are. Then if they are, then q has to divide their difference. But by assumption, the greatest common divisor of p and q is 1, and which means q has to divide the difference k minus k prime. But remember, these numbers go up to q minus 1, so it's not possible for q to divide the difference, so the values have to be distinct. So now let's suppose that one of these is congruent to b mod q. Again, q has to divide the difference, and if the greatest common divisor of q and b is some number d, then d also has to divide kp plus r. So the greatest common divisor of q and kp plus r is something d or larger. This means that if kp plus r is congruent to b mod q, and the greatest common divisor of q and b is not 1, then the greatest common divisor of q and the number isn't 1. And so the greatest common divisor of qp and kp plus r isn't 1. And so we should strike these numbers as well. And that means the only numbers that could be left in the column are the numbers that are relatively prime to q. And so this leaves phi of q entries in each column. Now, this is a fairly complex set of reasoning, so remember, concrete doesn't hurt. For example, we can try to find phi of 36 again. So remember, we wrote 36 as a product of relatively prime numbers and set down a grid. The numbers 3, 6, and 9 are not relatively prime to 9, so we eliminated those columns. Consider any remaining column, like 5, 14, 23, 32. We note that these numbers taken mod 4 are, and so we see that the remainders are distinct. And since the greatest common divisor of 4 and 2 is not 1, and the greatest common divisor of 4 and 0 is not 1, we eliminate these two entries. And this leaves phi of 4 two entries in each column. While it's true we will only have phi of p, phi of q entries remaining, are they guaranteed to be relatively prime to pq? So let kp plus r be one of the remaining entries. We know the greatest common divisor of p and r is 1, since otherwise we would have eliminated the column it's in. If the greatest common divisor of kp plus r and p is d greater than 1, then d would have to divide p, kp plus r, and so d divides r. But if d divides p and d divides r, then the greatest common divisor of p and r is going to be at least d, and so the greatest common divisor of kp plus r and p must be 1. Also, the greatest common divisor of kp plus r and q has to be 1 because we eliminated any entry in the column that had a common factor with q. And so our greatest common divisor with p is 1, our greatest common divisor with q is 1. But now, and here's the point, suppose the greatest common divisor of the number and the product is something greater than 1. Well, let s be a prime factor of d, then s divides kp plus r, and s divides either p or q, where, remember, it can't divide both because p and q are relatively prime. But if s divides kp plus r and p, then the greatest common divisor of kp plus r and p is at least s, and we know that's not true. And if s divides kp plus r and q, then the greatest common divisor of kp plus r and q is at least s, and again, that's not true either. And so it follows the greatest common divisor of the number remaining, npq, must be 1, and this means that all the remaining entries must be relatively prime to pq, giving us the theorem, if the greatest common divisor of p and q is 1, then phi of the product is the product of the phi values. For example, let's find phi of 120. So we note that 120 factors as 2 cubed times 3 times 5, and so 2 cubed and 3 times 5 are relatively prime, so we can split. 3 and 5 are relatively prime, so we can split them. 2 cubed is a power of a prime, so we know how to find phi of 2 cubed. 3 and 5 are both prime, so we know how to find phi of 3 and phi of 5, and we can multiply them together to find phi of 120.